let's see how it goes. Dot R, well, R is basically along the x-axis there, right there, in the I-hat direction. And so I end up with I-hat dx. That's basically my dr specifically for this problem. Well, I-hat dot I-hat is did somebody say it? I missed it?
I-hat squared.
Which would be?
It's just one.
Steve?
Just one.
Yeah, it's one. Any vector times itself is just the magnitude squared. Sorry, let's correct that. Any vector doing a dot product with itself, it's just the magnitude squared, and the magnitude of a unit vector is one, so it's just one squared. So this becomes negative integral k lambda L x times x plus L dx. So I'm integrating from, well, basically the extremes of x. From infinity to x. Now for the pure mathematicians, this is potentially troublesome, and I can just make that x prime, and x prime, if that makes you feel better. But in physics, it's tradition, or I wouldn't say tradition, it is common practice, that's probably better, of just recognizing this x is a variable and that x is some specific location. These x's are not officially the same. So the question is, how do we integrate this? Well, I've got, pull the constants out, I get k lambda L, infinity to x, of 1 over x, x plus L, dx. So how do we integrate that? Besides looking it up.
Partial fractions?
Yeah, the U, wait a minute. It was like U, V equals U times prime V.
Oh, okay. So you're going for UV minus integral of VDU, something like that?
Yeah, that's it.
What would you set U and, so that would be, all right, so integral of U dV is equal to UV minus integral of V du, or flip your U's and V's if you need to. I can't remember what I just said, or. So what would you establish as U and what would you establish as dV?
So U be X and B would be X plus L.
So you're establishing dV is,
X plus L.
the dV's gotta have an integral in it, or a differential in it. I think a simpler route was something Gage said.
Partial fraction decomposition?
Yeah. I'm gonna leave the L in there actually. So I have L over x times x plus L is equal to some number over x plus some number over x plus L. Is that what you were thinking?
Yeah.
Yeah. If we multiply everything by the common denominator, we get L equals A times x plus L plus B times x. So I get AX plus AL plus BX equals L. And so looking at the L terms, A equals 1. And then I get A plus B times X. I don't have an X term over there, so A plus B equals 0, which means B equals -1. And so this breaks up into one, let's see, okay, so this is integral of 1 over X plus 1 over, oops, minus 1 over X plus L. Did I make a mistake?
No, that looks right.
I originally thought about doing it that way, and then I realized this
Yeah,
might
it
be
takes
simpler.
too long.
It's quite possible you could do it this way. It
Just
just,
takes too long.
as with anything, it's the way your mind's working at that moment. So, write our value for V over here. Lambda K, natural log of L plus L plus B, right? All right, oh, negative K lambda. So now I'm gonna do each one separately, and so we get negative K lambda times the natural log of X from infinity to X minus the natural log of X plus L oh, that's why I did it that way. I knew there was a reason for it. I'm gonna keep that together. So this becomes negative K lambda, natural log of X over X plus L. Which would be negative K lambda, natural log of X over X plus L minus negative K lambda, natural log of, stick infinity in there, and you basically get 0. You get 1. Yeah, somewhere messed up. Oh. Which equals K lambda times the natural log of X plus L over X, there we go. Which is K lambda, natural log of 1 plus L over X. From infinity to X. Now you stick the X in, you basically get this, the K lambda natural log of 1 plus L over X, minus, you stick infinity in, this L over infinity is close enough to 0, so we basically have the natural log of 1,
Which is 0.
and then, which is 0, so this minus 0. And so we end up with the value for V.
Oh my goodness.
Now, in this particular case, this was a whole lot simpler, just to do the integration in my opinion. However, it doesn't always work that nicely. Sometimes this is easier. And we also have the reverse process of, if I have V, how do we find E? Because we got a nice integral right here. Surely, there's a nice little derivative we can do. It does require slight hand waving in some directions. But questions before we tackle the other way? I'm not going to go through this, I'm just going to hope that you trust me. Or if not, just say so, and then we'll do a derivative of this to see if we get that. Oh, no, sorry, derivative of that to see if we get that. All right, so we have this relationship here. Well, we can also write that change in V from some initial potential to some final potential of dV is the integral, negative integral from some initial location to some final location, E dot dr. In essence, we get dV over dr negative is equal to E. And the direction thing has sort of disappeared right there, and we can rationalize it, but ultimately, r hat. Now, in this example right here, we in theory should be able to find the electric field by doing, since that's in the x direction, negative dV dx I hat. And we'll get that answer that we had over there. But this also tells us if I have a graph that is of the potential, all I have to do is take the derivative, flip it upside down because of the minus sign, and I now have a graph of my electric field, assuming it's a one-dimensional problem. So let's do it. This is my potential with respect to R. So I have some sort of charge distribution such that my potential is, it relates to how far I am away from that source. Looks like that. What does my electric field look like? And as with any graph, doing it this way, let's figure out where the zeros are. I know my electric field is going to be based upon the derivative. So where's my electric field equal to 0? All right, going with the hand gesture, so we got this point right here. Let's see if I'm actually somewhat lined up there. Got this point right here, and that point right here. My electric field in this first segment, well, what can you tell me about the slope or the derivative? Not looking for a sophisticated answer here. From this region, from here, from r is equal to 0 to the first peak, what can you tell me about the derivative of potential?
It's decreasing.
Okay. And positive or negative?
Negative.
One of you is right. You said negative, you said positive,
That's it, positive.
and fine.
Strictly a guess, I don't know.
How do you know if a slope is positive or negative?
I thought it'd be decreasing if it's going down.
Sorry, you heard two different things there. So, sorry,
If it's,
Yvonne?
if it's decreasing, I thought it was be going away, like the electric field would be, I guess.
Okay, so you're thinking through the physics of it,
Yeah.
and there was someone else.
Direction is negative, then it's negative down. So it's decreasing, but it's not negative until it goes down.
Okay, so the fact that it's going this way,
Oh,
Yeah.
I see.
is that what you're going for?
Yeah, it's
Current.
positive.
Yeah, that's for my mind was, remember the slope is rise over run on a very simplistic level. If it's going like that, it's a positive slope, that's a negative slope.
Okay.
Yeah, you're thinking way up here, but you needed to bring it down. Now, so my slope is positive here, but my electric field has a minus sign right there, so this becomes negative
Okay.
for my electric field. I was also wondering when you said negative, whether you jumped ahead a step. It's getting closer to 0 as well, actually hit 0 at that point. Now, what the shape looks like, it's negative, becomes less negative as we get closer to the axis. Well, it has to connect here. Also, we can look at it from the point of view as the slope is negative, therefore the electric field is positive. And then in the next region, negative, the steepest was somewhere around there. And then we get this big drop off there. Negative slope, electric field is positive. And it looks like it peaks somewhere around here. Something like that. It is a crude sketch. So now, at this location right here, I'm gonna put a positive charge. Which way is that positive charge gonna go? We got two different ways of looking at it. Pick one and run with it.
Downward because the electric field is down?
It'd be left or right.
Oh.
So downward, is that you're saying left?
I don't know yet, hold on.
Okay. I guess technically I put the charge here. That's just what the potential is at that point, and that's what the electric field looks like.
Could be to the left because it wants to minimize its potential.
Okay? So from a potential point of view, the positive charge wants to go to a lower potential, so it will move left. From an electric field point of view, my electric field is negative there. So my electric field is pointing towards the source. And positive charges, when they sense the electric field, go in the direction of the electric field. So again, it's going to be going left. If we got different answers, then we knew we had a mistake somewhere. Now suppose I put a negative charge right, well, basically at this location right here. And then I just give it a little tap to the left. What's the negative charge going to do?
Are you saying like it's in the very center of that?
Yeah, so at the point where my electric potential is at its peak, I put a negative charge at that location and just tap it a little bit to displace it.
Well, it won't go to the left.
So it'll just keep going?
It won't keep going, but it'll go until it's negative.
So it'll go until
Right there.
here?
Yeah.
And why?
Well, it seems like since the positive wants to lose its energy and go to the left, it seems like the negative would also want to do the same thing.
It does want to lose, well, it depends on how. When you say lose energy, what do you mean?
Lose potential energy.
Okay, so yes, I will agree, the negative charge wants to lose potential energy. So why does losing potential energy means it keeps going to the left? All right, so let's just drop back for a second. Why does it want to lose potential energy? What's the rationale for that statement? I mean, it's right, but what's the rationale? Open to everybody.
It doesn't necessarily want to move towards zero, which is what it wants to get more negative instead of like losing.
Wait, say that again?
So if I'm thinking about it right, isn't it, it's not necessarily that it's gonna move towards zero potential, it's gonna move towards like a lower, which could be negative?
Oh, true, it's gonna lose potential energy.
Yeah, well, I was thinking that it would move to the right, in that example up there.
Right, so I got two questions on the floor now. So first off, why do we know that it wants to lose potential energy? Why does anything lose potential energy?
Because it's sat there too long. It's like your batteries go dead.
I was thinking of something different. All right, so if I take this marker and I let go of it, it lost potential energy, gravitational potential energy in this case. What happened? Where did it go?
Another force acted upon it.
Okay, that's why there was some shift in energy. A conservative force acted on it, therefore the energy transformed into a different type. Okay, so it lost potential and it gained kinetic. It's that whole balancing. As long as the force that's involved here is conservative, if it loses one, it's gonna gain the other. Conservative forces cause the transfer of, or change of energy from one form to another. Non-conservative forces cause a transfer from one object to another. But here, we're dealing with electricity and electric forces, so this is conservative. Energy should be conserved. So if I tap it to the left, so I introduced a non-conservative force to it to give it some energy, or at least some kinetic. It gets to this point, if it keeps going, it's gonna gain kinetic, which means it has to lose potential. Or if it comes back this way, that means it hit some point and then came back. So there was a moment where the kinetic was zero because it stopped in order to come back. And once it stopped, it would want to lose potential again because it's gonna gain kinetic.